Okay, so let's continue. So last time we sort of derived and proved the bosonic commutation relations, and the phonons and photons are examples of bosons, and they are simply just related to the harmonic oscillator vibrations. And we will look at those phonon vibrations in the next few lectures. But before we study phonons, and we should learn first this very famous and well-known phenomena called Bose-Einstein Condensation, or BEC. And this phenomena has a long history. Okay, it was traced back in the early 20th centuries, like 1924. Einstein actually received a manuscript sent from Bose, is the theoretical physicist in India, and he discovered first that bosons actually tend to occupy in the same ground state macroscopically. So at ground state, all the bosons will get condensed into the same many-body ground state, and nowadays we call this Bose condensate. But back then, Bose simply just derived from statistical mechanics that there is such a new phenomena, and then Einstein really got impressed by Bose manuscript and managed to translate this manuscript into German, and Einstein published this paper in a very famous German physics journal called Physics in 1924. And after that, people got interested in searching for the signatures of this Bose-Einstein condensation. But because the temperature that happens to have such a BEC phenomena is really, really low, I don't know how low is that, say at least micron Kelvin, at least. Okay, but the technology that lead to such a low temperature was not ready. Okay, until various smart experimentalists that managed to use laser to cool this atom down to the very, very low temperature, like even lower than this 10 to the minus 3 Kelvin, maybe I don't have the correct number of that low temperatures. And then in 1995, experimentalists by Cornell and Wyman in US laboratory called Nist and Gilla, and they realized for the first time this called atoms to get Bose condensed into macroscopic huge wave functions called this macroscopic Bose condensation, and they really saw this huge spike of this macroscopic wave functions that come from the accumulation of those bosons at ground state. So you can consider this as a collection of many boson wave functions, and they overlap. And millions of bosons get Bose condensed at least low enough temperatures. When they overlap, form a huge macroscopic wave function called this Bose condensed state. And this scale of this macroscopic wave functions is of order of this de Broglie wavelength. Okay, the de Broglie matter wavelength is actually a huge macroscopic scale. It's not microscopic in the sense that it is not Armstrong, but many order of magnitudes larger than the say atomic scale. So we can really see this condensate wave functions experimentally from this coatom experiments. Okay, so today we will theoretically go through this similar steps as that went through by Einstein and Bose from statistical mechanics, and also from the commutation relations of bosons, that we could conclude that as temperature decreases to 0, and all the bosons could form such a macroscopic large-scale wave function. So we already defined this destruction and creation of a single boson in this many boson state, 5,0. Presumably this 5,0 is just the BEC wave function 5,0 here, which contains n boson, and n is really, really large. can go to 10 to the 23, that many atoms. And then it followed this the rules that we define to create or destroy the single boson from the many boson state. And those boson operators satisfy the commutation relations. And we assume that those bosons are non-interacting, meaning they have such a kinetic energy with a quadratic dispersion, the same dispersion that we studied free electron gas. But instead of the fermion operators, here we are talking about the kinetic energy of free bosons. Okay, so we will see later that based on the simple, kinetic energy Hamiltonian, and we could verify and derive that as you lower the temperature, the occupation of bosons that stay in the ground state increases dramatically and reach to a macroscopic level. But let's just look at the statistical mechanics. So if you sum over the occupation number for such a bosons occupying, say, finite momentum or zero momentum, and you'll get total number of bosons, right? Okay, so K runs from, say, 0 to all the way to infinity. And we know very well that this occupation of boson satisfying this Bose distribution function, where you need to sum over this Bose factor, where this represents the probability density to find a single boson at the state K, right? Where K is the momentum of the boson. So this minus sign in the denominator, which dramatically changes the outcome of the summation compared to the fermionic case. So you will see that as you lower temperatures, the occupation that occupy zero momentum diverges, right? Because of this minus sign here. But let's just try to do it. We could use the integral, instead of a summation, to sum over all this occupation of bosons. Here's mu represents the chemical potential, which is the energy required to add or remove one boson. And we can define this number density, little n, which is the number of bosons per unit volume, and this is the integral of this Bose factor. And of course, you could convert this moment integration into energy integration following this density states inserted in this integral. So you could simply just change this integration to the energy integration instead of a moment integration. Okay, and this rho as function epsilon is actually inversely proportional to the derivative of dispersion with respect to momentum. Remember, from the solid state 1, the density of states of your, say electrons or bosons is proportional inversely to the derivative or slope of your dispersion with respect to the momentum. And then we could start to look at this energy integration from 0 to infinity, this factor here, and later we will analyze this integral carefully and see this BEC phenomena occurs as you lower temperature. Okay, so what we do is to introduce new variables that give us more convenience. Suppose z is defined as e to the beta mu, and x as beta times epsilon. Then the this number density n as a function of the integral energy integration now becomes much simpler, because now we should deal with just dimensionless integration, because the x is dimensionless quantity. So x is defined as beta times epsilon, where beta, very well defined as 1 over kBt, has a unit of energy, and epsilon is also energy, so beta is 1 over energy, and therefore x has dimensionless. S is dimensionless quantity. And so this integration could be done semi-analytically and following some kind of mathematical trick. Okay, so later we will Taylor expand this quantity here in the integral, because for z is actually less than 1 and integral is actually convergent, and we are able to Taylor expand this in terms of those functions of power series of z. Okay, so let's take a short break. When we come back, we will Taylor expand this stuff here. And the square root of x comes from the density of states. So if you really take care of dispersion and the slope of the dispersion, and you simply can convert this into a dimensionless quantity x, and that will lead to the square root of x here. Okay, so let's take a short break. Okay, so for z e to the beta mu, for suppose z is actually less than or equal to 1, or mu is actually negative or 0, then this z is actually less than or equal to 1, right? Because e to the minus some positive number is actually always smaller than or equal to 1. So in such case, this factor, this complicated factor, is actually convergent, meaning for any z over x, this factor would not diverge. And therefore, you could Taylor expand this factor when z becomes less than or equal to 1. When you Taylor expand this factor, you could collect all this factor of z times e to the minus x. Of course, e to the minus x is also a factor less than or equal to 1, because x is positive, and e to the minus positive number is always less than or equal to 1. Okay? So you get a summation over infinite number of terms in order of z times e to the minus x. And this numerator, z times e to the minus x, you can simply just pull them out of this bracket. And so inside the bracket is this inverse 1 minus z times e to the minus x, right? So this is just a geometric series. And you could reorganize these terms in a summation over this factor, z to the power of p times e to the minus px, where p runs from 1 to infinity. So if you plug in this p here from 1 to infinity, and you expand all the terms in a summation, and you return to this infinite number of terms in a Taylor expansion of that factor. Okay, so we will take advantage of such Taylor expanded terms and rewrite this integral in terms of this different form that involves these two factors. And therefore, remember our little n, which is the number density, is given by this. Let me just repeat this. So now we simply just Taylor expand this stuff, right? And you can simply just replace this complicated functions of z and x in terms of this summation over this product of these two factors. And we will simplify this in just a moment. Okay, so suppose that I simply just plug in this Taylor expanded form of that stuff inside the orange circle, and what I get is the following. And I will collect the most important factor in the integral over x, which is e to the minus px times square root of x. So since this is the integration over x, so it has nothing to do with z when you perform the x integration. So I simply just focus on this integration over x, and this is the term that I should evaluate in terms of the x integration, and I could rewrite this, which is e to the minus y square root of y and dy. So you could verify that by change variables that you are able to get to such a conversion, and this is given by this result, because this integral is actually a gamma function, 0 to infinity, and gamma 3/2 is actually square root of pi divided by 2. So I guess the only tiny little gap that between these two is how you convert this integration over x into integration over y. So then now this little m becomes this times a special function called g 3/2 as function of z, where this g 3/2 as function of z is actually sum over p from 1 to infinity and z to the power of p times p of 3/2. For z is less than 1, this is converged. For z is greater than 1, and this integral diverges. So now let's look at the analytical properties of this g function. G 3/2 as function of z, where z is 1. This is this summation, and this is a well-known result, which is called a Riemann zeta function of 3/2, which is 2.612. And this Riemann zeta function is defined as sum over p from 1 to infinity, 1 over p to the power of s. And later we'll take advantage of such a Riemann zeta function and to really see and argue that there's something happened when mu equals 0. And we come from high temperature where the chemical potential is negative, and we will also prove that the chemical potential should be negative at high temperatures. And then as we lower temperature, the chemical potential becomes less and less negative until certain temperature low enough that the chemical potential becomes 0. And when chemical potential becomes 0, this is the temperature where the bosons get condensed, because at or below that temperature, it doesn't cost you any energy to add one more boson in your many-body state. As a result, and more bosons would like to get condensed as a macroscopic condensate, and that's the origin of a BEC. But before that, let's just continue analyzing this function g 3/2. So if I take the derivative of the g 3/2 as function of z, I get this, and as z approaches 1, and this derivative diverges. So I could numerically calculate this Riemann zeta function, g 3/2 as a function of z, and you will see immediately that this function takes a value of 0 when z is 0, and then suddenly as z becomes 1, you experience upper bound for this g function. But if you take the derivative of that g 3/2 function right at z equals 1, and you get divergence. So this is really sharp. So the slope of this function, taken as z equals 1, is actually infinity. So this is something that is a signature of a BEC when z hits 1, so which means that what z is e to the beta mu. When z goes to 1, which means that mu will go to 0. Because beta is a temperature, inverse temperature, it cannot be 0 infinity, so the only thing that makes z being 1 is the vanishing of the chemical potential. And which means that as you lower the temperature, z is going to hit 1. And when that happens, something dramatic occurs. And that is signature of a BEC. So let's take a short break. When we come back, we continue finishing this calculation. So let me just close up the gap. Okay, so between these two integrals that I just mentioned, right? So on the left-hand side, this is the integration over x. On the right-hand side, this is integration over y, whereas y is defined as p times x. So if you those change of variables as you study in your calculus, and you will see that there is a p to the power of 3/2 appearing in the denominator. So you simply just replace x by y over p. Okay, so dx is dy over p, and x is y over p. So there is a square root of p here, pick up here, and there is a factor of 1 over p pick up when you interchange x to y, and altogether you get p to the power of 3/2. So now we close the gap. So you could convert this integral from x to y, and then as I mentioned, now this number density n is a function of this temperature and this g 3/2 function, right? This Riemann zeta function as function of z. Okay, so now we could determine the chemical potential by this relation. Okay, so you fix the temperature and the number density, and then you could solve for Z and therefore mu. Okay, so let's look at the chemical potential at high temperature. As I mentioned, the chemical potential at high temperature should be very negative. So you could Taylor expand this G3 has function when beta goes to 0 limit, or temperature is infinity limit, and which is about Z. Okay? Well, you could easily see that from our earlier definition of the Riemann zeta function, G3 halves, when beta goes to infinity, and Z is finite. Okay? So then this, at first non-vanishing order, this G3 halves function is approximately given by Z. Of course, there's some other higher order term which we don't care. In that limit, mu is actually close to minus infinity. So remember this G3 halves as function of Z behaves like this and suddenly jump to some number. So when beta goes to 0 or temperature goes to infinity limit, the Z is actually in what limit? Close to 1, right? And in that region. So you could easily convert this relation to get chemical potential, which is minus 3 halves kBT times the log of this vector. And this actually agrees with our expectation that when T is really, really high, remember this chemical potential is actually carrying a minus sign in front. And here is the log of that mkBT divided by this stuff. And if T is really, really high, then the log should be very large, positive value, right? But this overall mu is actually carrying an overall minus sign here. So it's really, really large and a negative value. So it is a large negative value minus almost magnitude of infinity. This is precisely what we expect, because in order to satisfy this both statistics at high temperatures, chemical potential should be negative, very, very negative. But we will see in just a moment that as you lower temperature and your chemical potential come from very negative value, but now it shrinks its magnitude more and more as you lower the temperature more and more. And at the end of the day, when you lower the temperature enough, and you will get mu equals to 0 or Z close to 1. So I apologize. This this region is not when Z close to 1 at the beginning. It is close to 0 here. So as you notice that Z is actually e to the beta mu, right? So when beta close to 0, however, as we just saw here, this mu is actually very large negative value, okay? And therefore, this mu is actually minus a very large positive value, and then you actually combine these two factors, so you get e to the minus a very large value, which is almost 0. So I apologize for this typo error. So in that limit, high temperature limit, this G function is actually restricted to the very small Z value, close to 0, and therefore you are allowed to Taylor expand this function here when Z is close to 0, and that is actually a linear in Z as a leading order contribution. And then from that, you get this very large negative value of chemical potential, which is actually consistent with our expectation here. Okay, so next we will derive the BEC phenomena from this property that we come from a high temperature where chemical potential is very large negative value, and then when we lower temperature, the magnitude of the chemical potential mu decreases, and so as you lower temperature to some temperature, which we call Tc or TBEC, then the chemical potential is almost 0. Okay, so let's see how this occurs. So suppose we find such a Tc where chemical potential is 0, and you could estimate this condition, and the consequence of that condition to satisfy Okay, so as I mentioned, when z goes to 1, this Riemann zeta function, when z equals to 1, gives you a finite value, which is 2.6. Okay, but this is also given by, on the right-hand side, this complicated function of temperature h bar, kb, and also n0, where n0 refers to the number density in the BEC state. So you can very clearly see that in order to satisfy this condition, this Tc has to be around that value. And this is called TBEC, or BEC temperature. And while you could estimate how large or how small this TBEC is, and it turns out that in order to satisfy this condition, this TBEC is really, really low. And also, this N0 here reaches the macroscopic value, okay? Which means that this N0 takes a very large value. To cancel the vanishing of the denominator, as T is actually lowered, N0 becomes a fixed value. As you lower temperature continuously, this N0 will increase. So let's just look at the behavior of the chemical potential as a function of temperature. So in principle, you could numerically solve this equation over here. So now you have many computational tools that help you to solve this equation. Okay, so I guess back to the early 20th century, where a computer was not invented yet. Okay, so people could only use, a piece of paper and pen to really, or integration tables to actually solve this. But nowadays, you are able to use whatever resources you have to numerically solve these equations self-consistently. And let's just look at this numerical solution. And as I mentioned, if temperature is low enough, then the chemical potential tends to vanish. And let's just make a plot of such a critical temperature, Tc or TBEC. And at the end of the day, when you solve this, this equation over here, and you will find that the solution is the following curve that I plotted here, that when temperature is high enough, the chemical potential is very negative, and then it starts to shrink the size in the magnitude, and then approach to 0, and at TBEC, and the solution gives you the 0 of chemical potential. Meaning, starting from this TBEC and below, it doesn't take you any energy to add one more boson to the system. The chemical potential vanishes. So let's just look at what happens when T is less than Tc. So when T is less than Tc, so all particles tend to be in the same macroscopic ground state. And in that case, mu is actually 0. And this TBEC is the temperature where this N0 starts to grow. So when temperature is larger than or higher than Tc, this N0 is actually going to almost 0. Which means that when this temperature is higher than this Bose condensation temperature, no bosons will get condensed, meaning there's no N0 that satisfies this condition when temperature is larger than TBEC. Okay, so let's stop here for today, and on Wednesday we will continue just analyzing the remaining part of this BEC phenomena, that we start from this plots that is the solution of this equation over there as a function of temperature and chemical potential, and we will estimate how many bosons are in the condensate state and how many bosons remain in the excited states as you lower temperature. Okay, so at this TBEC, the bosons start to get condensed, but not all 100% bosons get condensed. But when you lower the temperature more and more until you reach the 0 temperature limit, and almost 100% bosons will be in the BEC. So we will continue on Wednesday.